Welcome to myprojectbazaar.com.
Now we discuss about the product for toward on FPGA hardware implementation of the Almaty forecast to space-time block coding. Next we see the abstract for the product. Wireless communications applications such as cellular, 4G, broadband internet, video and audio streaming has permeated into every aspect of modern life. To support these applications, extensive research has particularly been conducted on multiple input and multiple output systems. In the recent years, MIMO system exploits spatial diversity and increase the channel capacity without requiring greater transmission power or at the expense of bandwidth. Multiple transmit and receive antenna are currently used to significantly enhance the performance of wireless communication of the MIMO system. Space-time block coding has risen as one of the promising candidates in exploiting the spatial diversity. In the recent years, space-time block coding has attracted the attention of the research community in the quest of optimizing the use of the bandwidth to support today's wireless communication application. To achieve the aim, STBC exploits the spatial diversity. However, the complexity challenges excitable when more than two transmit and more than one receive antenna are used. This paper presents a implementation of a low complexity maximum likelihood decoding complexity of the double. This design exploits and takes advantage of the enhanced processing capability of an FPGA to achieve this aim. The scheme was first coded in MATLAB then in ModelSim, but we implement the Xilinx for the VHDL coding to develop our MIMO FDM system. Next we see the flow diagram for the project. First of all, we design the hierarchy based tree architecture design in overall architecture. The VLSI MIMO FDM process is developed by the VHDL coding. The VHDL coding is developed by the structural modeling for our MIMO FDM process. First, we design the MIMO FDM architecture. MIMO FDM architecture consists the IBM and BCM blocks. IBM blocks means input pre-processing module. BCM blocks is parameter calculation module. The two block module is mainly focused by the digital architecture design. The IBM block consists of two sub-blocks, STBC and non-STBC work. STBC is mean space-time block coding, non-STBC non-space-time block coding block. These blocks controlled by the controller block. First, we design the IBM block in our architecture, MIMO FDM architecture. The IBM block consists of two channel allocations for the STBC and non-STBC. The IBM is one of the channel allocation block. Channel allocation block is mainly used to the input signal is passing to the STBC non-STBC. We select the channel, then passed to the STBC output or non-STBC output results. This work is controlled by the controller architecture block. Thus the block is using to the IBM works. Then IBM result is passed to the parameter calculation module. This parameter calculation module is mainly used to the calculate the overall signal parameter results in our IBM block final results. The IBM blocks just direct the channel output result. Thus the result to apply the BCM block. BCM block is considered the squarer and multiplier, then XOR gate blocks and register elements. These logical elements are applied to the BCM block. So first we design the multiplier and squarer unit for the BCM block, then we design the XOR gate operations, and to apply the register element then we design the BCM block, and finally we connect the IBM and BCM block using to the overall MIMO architecture. Then first of all we design the IBM, and second we design the BCM, then apply the input date channel result and the channel allocation and the channel input, then clock pulses for the MIMO FDM architecture, then pass the IBM block, and finally we detect the channel output for the IBM block, and to apply the BCM block, then BCM block we calculate the parameter output module for the final result. These results are to get the output final result and to simulate and synthesis for the Xilinx OFDM Xilinx 14.2 software. The simulation is only calculate the manual results for applied the input and output result. The synthesis report is calculate the satisfy the three parameters: area, power, delay, speed operations. These parameters to satisfy for the synthesis report. Finally, we see the output for the product. First of all, we open the MIMO design Xilinx ISC project. Then select the simulation and to select the simulate behavioral model. Just we open the ISM simulator for the simulation process. Then create the simulation result. Just we apply the binary input result and to get the output final result for the MIMO OFDM process. Then apply the input for the clock signal and set the reset function to deactivate the enable function. Then apply the channel selection and channel count for the IBM and BCM process. Then to apply the binary process input results for the channel data, any of the 8-bit data to apply the channel input processor. Then apply the input selection signal for two 8-bit data signals. Then to run the time specified on the toolbar. Then apply the clock 1 logic. Then run and apply the another clock signal to in MIMO OFDM process. Then deactivate the reset function and activate the enabling function. Then set clock 1 logic. Just we calculate the zoom to full view functions. Then create the D1 to D3 function for the OFDM process and we calculate the parameter calculation module result for the output process. Then close the simulation result and we calculate the synthesis report result. Just we select the implementation and you run the view RTL schematic diagram. Then add and create schematic. Just double click the block. This RTL diagram represent the what are the logical blocks present in the MIMO OFDM process. Then calculate the view technology and calculate the view technological schematic diagram. Add and create schematic. Just double click the process. Then create the IBM block for the view RTL schematic diagram. This schematic diagram which represent the what are the lookup table and input output, bounded input output and wire length and wire connections, and then flip-flop pairs placement for the technological diagrammatic representation. Then go to the design summary process. Just we select the synthesis report result and down of the report we calculate the area of the MIMO OFDM process, the slices LUT and flip-flop pairs, then bounded input output. To calculate the area of the OFDM architecture process. Then calculate the timing summary results. The minimum period is 7.298 nanoseconds and frequency level is 137.031 megahertz. Then latency level to be after and before clock calculations. The delay time is 2.091 nanoseconds process. Just then finally we calculate the power calculations for the process. Just